Welcome to the CDC's training program on the use of handheld radiation survey equipment. I'm Dr. Armin Ansari, a certified health physicist at the CDC. The purpose of this program is to provide training on how to use handheld radiation detection equipment to screen people who may have radioactive contamination on their skin or clothing. After a large-scale radiation incident, individuals from a variety of professional backgrounds may be asked to help with such screening. This is often referred to as a radiological survey. Ideally, this role should be defined in your emergency response plan, and the task should be assigned before any incident happens. Training in the use of the equipment should be conducted as part of your emergency preparedness planning. To use this training video, however, it's not required that you have any prior familiarity with radiation survey equipment. So in a pinch, this program can be used as a just-in-time training tool. If you have some familiarity with radiation survey equipment, you may use this program as refresher training. You may also want to review the supplemental material on this DVD on the use of alpha synonation detectors and ion chambers. Now, please remember that individuals with specialized training, such as health physicists, medical physicists, or radiation safety officers, should guide the overall radiological survey process and assume responsibility for meeting screening standards and making judgment decisions about triage. Before learning about the equipment, it helps to understand the difference between radioactive or radiological contamination and radiation exposure. If this basic radiation principle is unfamiliar to you, take a moment, please, to review these terms. You can do this by viewing a short 2-minute animated film entitled Radiological Contamination and Exposure in the Supplemental Resources section of this DVD. Now, let's begin our introduction to radiation survey equipment.
Welcome. I'm Sarah Roberts, a certified health physicist with the Oak Ridge Institute for Science and Education. It is my pleasure to introduce you to the radiation detection instrumentation typically used to survey people for contamination. These instruments are Geiger-Müller, GM, or Geiger detectors, and within this class there are several principal types. As you can see from this display of instruments, there are many companies that manufacture instruments, so they come in all sizes, shapes, and colors. Some of you may not have seen these instruments or be familiar with these terms I just used. Therefore, let's take a look at these detectors in a bit more detail. When monitoring people for radioactive contamination, very sensitive detection instruments are necessary. Survey meters, especially Geiger counters, serve this purpose well. Survey meters are the handheld instruments most commonly used to measure radiation. They are frequently referred to as radiation detectors, survey meters, or friskers. This kind of detector has several possible uses: locating gamma-emitting sources of radiation, locating contamination on people and equipment, and establishing control boundaries at an incident scene. The best GM to use when looking for contamination on surfaces is the pancake GM because it has a very thin window, which allows even beta radiation to be detected. Geiger-Müller detectors, like any other piece of equipment you might employ in your line of work, have their good points and bad points. GM detectors are easy to use, easy to maintain, and are generally pretty rugged. They are almost always going to be your instrument of choice when you want to look for radioactive contamination on people. They have other applications as well. On the negative side, the window is easily broken, so handle it carefully. Before we consider how GM detectors are actually used, there are 4 important steps I would like to outline. First, check the batteries, cable, and detector to make sure all of them are okay. Second, take a background reading in an area that you know is not contaminated. The term background measurement refers to radiation levels that are already present in our natural environment. Third, while you are surveying, scan slowly and as close to the object as possible without touching it, so as to prevent contamination on the detector. And lastly, always remember to record your survey readings accurately. Now, with these 4 overall steps in mind, let's walk through the entire procedure. We've provided a step-by-step handout of this procedure in the inside cover of the DVD case. You may want to follow along with me with the written procedure in front of you. When you look at this instrument set, what you'll notice first is a count rate meter of some sort. You'll also see a cable with connectors on each end, and a long handle with a small pancake on the end, again with a very thin entrance window on one side. Now examine all of these items for obvious signs of damage, a broken window or frayed or broken wires, for example. Next, assemble your equipment by connecting one end of the cable to the meter and the other end to the pancake probe. With the meter on, wiggle the cable near the connectors to see if this causes erratic behavior of sound or the display. If so, the cable is defective. Now let's discuss the different features of this instrument. First, all instruments require periodic calibration and testing. Ideally, your institution will have a routine calibration schedule for your instruments. Therefore, there should be a sticker on the instrument with a current date of calibration. However, in the event of an emergency, if the sticker shows an out-of-date calibration, do not let that stop you from using the instrument. Instruments can still be used for emergency screening, even though they may be out of calibration. Go through the routine check of the instrument. If it's performing properly, you can use it for screening. But remember, this should be done only in an emergency situation, as directed by the person in charge. Okay, the first step in using a radiation detection instrument is checking the batteries. Dead or dying batteries are the #1 cause of problems for these instruments. For most instruments, checking the batteries will be done by either pressing a battery check indicator button or turning the control knob or range switch to battery or BAT. This instrument has a control knob, so rotate the knob in a clockwise direction from the off position. The first position to the right is usually the battery check. Turn the switch to that position. If the needle does not move to the position on the meter face that indicates the batteries are okay, you'll probably need to replace them. For this instrument, you can see that the needle is indicating that the batteries are okay. While we're talking about batteries, let me give you a few additional tips. It's not a good idea to leave the batteries in the meter for long periods of time, months for example, if you aren't going to use them. They can corrode in the meter and ruin it. Also, look at the battery terminals to see if they are corroded. If so, you might be able to clean them with the eraser on the end of a pencil. Do not use batteries that have been rolling around in a drawer somewhere that are unwrapped or have been removed from their original packaging. You should be sure to keep a fresh stock of batteries available for each use. Please remember that even though you may have installed new batteries, you should not forget to turn the range switch to the battery check position and confirm that they are okay. Let's continue talking about the range switch. As you continue to move the range switch clockwise, you are on the scale settings. The scale controls the sensitivity of the instrument. At its smallest scale, ×1, the instrument is very sensitive and can measure small amounts of radiation. Likewise, at its highest scale, ×1000, the instrument is able to measure higher amounts of radiation. When taking a radiation reading with this type of instrument, the reading on the display must be multiplied by the scale setting. Now let's look at the variety of displays that can be found on the instruments. They may display either in units of counts per minute, CPM, milliroentgen per hour, MR per hour or milli-R, microroentgen per hour, micro-R per hour or micro-R, or some combination. Instruments have at least one display and a variety of controls. Different instrument manufacturers will place the display and controls in different design configurations. The basic components will be the same, but they may be found in different locations on the instrument. Displays are either analog or digital. On this screen is an example of an analog display. The display has a needle that will move from left to right as the amount of radiation increases, similar to the way a speedometer needle moves from left to right as you increase the speed in your automobile. Different instruments may display different units, or the same instruments may display multiple units. When using a GM detector, always use the count per minute CPM scale. If your instrument does not have a CPM scale, then use whatever scale is displayed, but always remember to note the units when you record the results. When taking a radiation reading with this type of instrument, remember that you must multiply the reading on the display by the scale setting. For example, this instrument is reading 350 counts per minute. The instrument is set at ×1, so 350 times 1 is 350 counts per minute. Let's take a look at another reading. In this image, the needle is at approximately 280. You may think that the reading is 280 counts per minute, But remember to check the scale. Since the instrument is set at times 10, the reading is 280 times 10, or 2,800 counts per minute. This is a digital display. In this image, you see a numerical readout in counts per minute. You should now be ready to use the instrument. For our final and possibly most important subject, let's talk about how to use this instrument to conduct a survey. Most GMs have an audible output. One particle of radiation going through the window of the pancake probe produces one electronic pulse. One pulse produces one count or click. Let's listen to a typical response to background radiation. Again, this background radiation refers to radiation levels already present in our natural environment. Following a large-scale incident, you may have a lot of noise. Therefore, you may want to consider having a set of headphones plugged into your survey instrument so that you can hear the clicks. Also, eliminating the audible clicking noise may lessen the anxiety of the person being screened. While surveying, in addition to listening to the clicks, you need to watch the meter face to see if the count rate is changing. Your instrument is likely to have a toggle switch to select F for fast response or S for slow response. Make sure the toggle switch is set for F or fast response when surveying for contamination. Next, we need to conduct a source check to make sure the meter is working properly. With the meter on, place the detector close to the radiation source, such as a thorium-containing gas lantern mantle, an orange Fiesta ware plate, or a plastic button check source. With the appropriate range selected, probably times 10 or times 100, verify that the meter responds. It's not a bad idea to indicate the reading on a label and stick the label on the side of the case. That way, the next time you check the GM, you will know if its response is changing. Some rate meters come supplied with a convenient check source on the side and a label indicating what the meter response should be. In a pinch, if you need to use the instrument but you do not have a check source available, you can assume the GM is working properly if its response to background radiation is between 30 to 200 counts per minute. Depending on the environment and what type of building you're in, the background radiation level can vary. In the event of a radiation emergency, background radiation levels may be higher than usual because of environmental contamination. One of the first things to consider, this isn't a requirement but a suggestion, is wrapping the pancake probe with a protective covering. This will prevent contamination of the detector. You can use a rubber glove or a plastic bag or saran wrap, for example. Next, I'm going to take a background reading. Make sure your range switch is set to times 1. Note that the needle fluctuates at low readings, and this is normal. You can change the toggle switch to S or slow response to make a more accurate reading. I have determined that the background count rate is 40 counts per minute, or CPM. Now make sure you move the toggle switch back to F or fast response when surveying for contamination. Keep in mind that you should turn the detector on well before you get into a suspect area. If the count rate steadily increases to a very high level, the meter pegs at the maximum reading, and then the response drops off dramatically, the GM detector may have saturated and zeroed out. This can happen in high radiation fields, and you should leave that area immediately. Now let's conduct a survey. When surveying a person, hold the probe approximately 1/2 to 1 inch from the person's skin and systematically survey the entire body from head to toe on all sides. Move the probe slowly, about 1 inch per second. Try not to let the probe touch anything, and pay particular attention to hands, face, and feet. If massive numbers of people require screening, to avoid delays, it may be necessary to perform only quick-look spot surveys of the head, face, shoulders, and hands, the most likely locations for contamination. Under those circumstances, it may also be necessary to use a screening criterion higher than twice the background. This guidance will be provided to you by the appropriate radiation authority. Locate the point that produces the most clicks. Document those locations and the radiation measurements. In general, areas that register more than twice the previously determined background are considered contaminated. Now you have seen the GM in use, so this concludes the demonstration of the GM pancake detector. Let's review the 4 important points about using GM detectors. Remember, check the batteries, cable, and detector to make sure all of them are okay. Take a background reading in an area that you know is not contaminated. While you are surveying, scan slowly and as close to the object as possible without touching it to prevent contamination of the detector. And accurately record your survey readings. If you need additional information about this instrument, refer to the enclosed GM detector job aid.
We hope this training has been useful to you. Personnel with specialized training in this field, such as health physicists, medical physicists, or radiation safety officers, will provide you with additional guidance. You'll be given further instructions on how to adapt this screening to a mass casualty situation. For example, if massive numbers of people require screening, to avoid delays, it may be necessary to perform only quick-look, spot surveys of the head, face, shoulders, and hands, the most likely locations for contamination. You will also be given instructions on what screening criteria to use with your instruments. Again, please consider specifying who will perform radiological screening as part of your pre-incident emergency planning process, and incorporate pre-incident training into your plan. In the event of a large-scale radiation emergency, there will be a high demand for trained personnel who can perform radiological surveys to assess contamination on people and objects that are suspected of being contaminated. You will be performing a vital role and are to be commended for your efforts.
Now let's take a little time to consider scintillation detectors, another major type of instrumentation. This is a zinc sulfide alpha scintillator. Alpha scintillation detectors work as follows. An alpha particle deposits energy in the scintillator. The scintillator then emits a flash of light, and the flash of light is converted into an electronic pulse by a device known as a photomultiplier tube. One alpha particle, one flash of light, one electronic pulse, and that's how it works. These pulses are then registered on the meter as counts per minute, or CPM. Now for some specifics about alpha scintillators. For an alpha particle to reach the zinc sulfide scintillator and cause a flash of light, it must penetrate a very thin window of aluminized mylar. The light is then reflected to the photomultiplier tube, which is located in the handle of the probe. A major advantage of the zinc sulfide alpha scintillator is the fact that it only responds to alpha activity. It does not detect beta particles or gamma rays. And since there is relatively little alpha activity in the background, the alpha scintillator should read 0, 1, or maybe 2 counts per minute in an uncontaminated environment. If you have a higher count rate than that, you need to determine what is happening. Because of its low background count rate, the zinc sulfide scintillator is the instrument of choice for locating alpha contamination on people or other surfaces. As you might well discover, the major problem with alpha scintillators can be the false counts that occur when there are tiny holes in the aluminized mylar window. These holes might be hard to locate because they can sometimes be too small to be seen. Fortunately, once you know where they are, the holes are easy to repair. All it takes is a tiny dab of black paint. So don't forget to have a bottle of paint on hand, the sort you can get at any store that sells hobby supplies. Black nail polish is an even better choice because the bottle will come with an applicator. As always, you need to make sure that the instrument is working properly before you try to use it. By now, you should be reasonably familiar with how to do this. First, examine the device for visible signs of damage. Dents in the probe or damage to the window, for example. Next, check the batteries. Again, your meter will either have a range switch that you turn or a button that you push to check the battery condition. If the needle on the meter does not move to that position that indicates the batteries are okay, go ahead and replace them, and then repeat the battery check. Next, rotate the knob to the appropriate scale available and determine the instrument's response to a check source. As I mentioned before, a thorium-containing gas lantern mantle or a plastic button check source can be used here. When checking the alpha scintillator, be sure to remove the plastic cover from the probe, assuming that it has one. And if the check source is in a bag, remove it because alpha particles cannot even get through a piece of paper. The next step is to check background. Turn the meter on in an area where elevated radiation levels are not expected. And using the most sensitive scale, record the reading on the meter. As mentioned before, a typical background for an alpha scintillator would be 0 to 2 counts per minute. Finally, if you're going to use a zinc sulfide alpha scintillator, you need to check for light leaks. With the audio on, point the face of the probe towards a source of light, an open window or an overhead light, for example. If there is a light leak, the meter will register many pulses. Then you need to locate the hole in the window and cover it with paint. In a pinch, a tiny piece of black electrical tape can be used. Once you have determined that the instrument seems to be working properly, you are ready to survey. Now that we have finished looking at GM detectors, we are going to consider another common gas field detector, the ionization chamber. Ion chambers come in many different shapes and sizes. So how do you know that you have an ion chamber? Well, here are a few hints. First, an ion chamber does not have an audio output. There are no clicks. Second, ion chambers never read out in counts per minute or CPM. The display will either be in MR per hour or R per hour. And third, everything is housed inside one case. There is no separate probe that has to be connected to the meter with a cable. Here are two different types of ionization chambers. One has a digital readout, and one has an analog readout. While these different ion chambers might not look the same on the outside, they all use the same type of detector on the inside, an air-filled cylinder approximately 3 inches in diameter. The primary role of ion chambers is to measure the radiation exposure rate due to gamma rays. Ion chambers are usually considered high-end instruments because they are used to measure high exposure rates, let's say 1 MR per hour and above. An ion chamber has a thin window that is protected by a removable cover. When the cover is removed, the instrument can respond to beta particles. Nevertheless, in most situations, it's probably best to leave the cover on and to forget about its ability to respond to beta particles. After all, a GM detector is a better instrument for detecting beta particles than an ion chamber. In addition, leaving the cover open increases the risk that the window will be broken. Ion chambers do have some disadvantages. First, a typical ion chamber is not sufficiently sensitive to perform measurements at the low exposure rates that you are likely to encounter. Second, ion chambers have a very slow response time. You might have to wait as long as 1 minute to get an accurate reading. And if you are moving too quickly, you might find yourself in a high exposure rate area before the ion chamber has had enough time to respond and let you know what's going on. Finally, an ion chamber will read too high if moisture gets into the chamber. This is a common problem because most ion chambers are open to the atmosphere, and the atmosphere contains water vapor. To prevent this from happening, ion chambers are designed so that the air must go through a drying agent, typically silica gel, before it gets into the chamber. One thing you can do to help keep your ion chamber in operating condition is to store it in a sealed box or even a plastic bag that contains silica gel.
When we are near a source of radiation, such as radioactive material, we can be exposed to the radiation emitted without becoming contaminated by the source. One way to think about exposure is to consider X-rays. When you have a chest X-ray, for example, you are exposed to radiation, but you don't become contaminated with radioactive material. We can reduce our exposure to radiation if we are shielded in some way, for example, by standing behind a concrete wall, or keeping the radioactive source inside of a lead container. To become contaminated, radioactive material must get on the skin or clothing or inside of the body. For example, consider a dirty bomb, that is a conventional explosive such as dynamite that is laced with radioactive material. When the device is detonated, people could not only be injured by the blast, but become contaminated. External contamination refers to radioactive material on the outside of the body. When a person becomes externally contaminated, simply removing the clothing can remove as much as 90% of the contamination. Gently washing the skin and the hair can remove most of that which remains. If a person ingests or inhales radioactive material, it can become incorporated in the organs of the body, and this is called internal contamination. Depending on the type of radioactive material which someone is contaminated with, certain medications can be administered to accelerate the rate at which the material is eliminated from the body. Examples of such medications include Prussian blue and DTPA.